Hello and welcome to another video on the channel. Thank you so much for all the support that you've given the videos so far. This video is going to be on intrusion related gold systems as a whole and linking those observations to what we see in the Paterson Orogen, specifically the Havieron and the Scallywag deposits of Granites gold. So I'm just going to start by defining what a geological intrusion is. Now, for most of you out there probably know exactly what it is. However, for those that don't, a geological intrusion is typically a magmatic body or an igneous body that cross-cuts other rocks. Normally, we melt something in the subsurface, that magma then rises to the surface and erupts out of a volcano as a lava flow or volcanic rock. But if it doesn't do that and it ends up crystallizing in the subsurface, we call that a platonic rock. Okay? Now, obviously, on its way to the surface, you have to go through other geological layers to get there. And that's where the cross-cutting comes in. And that's where the intrusion bit comes in, because you've had to intrude through those layers, which are typically sediments, but can also be other igneous rocks as well. Okay, and so in the UK, actually, we have a lot of intrusions that you can go and see in the Lake District, in Scotland, but Cornwall is probably the best place where you can see these big, massive granitic batholiths that the Dartmoor granite, for example, is an example of. So we can characterize different intrusions based on the shape and the relationship that that igneous body has made with the rocks around it. So if the intrusion has penetrated through several layers of rock vertically, we call that a dike. If that igneous body has intruded horizontally along a layer, we call it a sill. And if we formed a rather lens-shaped or dome-shaped igneous intrusion that's caused a bit of uplift potentially in the sediment layers above, we would call that a laccolith. And normally these all spawn off of a central massive igneous intrusion called a batholith. And intrusions can range in composition. They can be more basaltic or mafic, but they can also be more granitic or felsic. And that will have relevance to what metals you might expect. And geological intrusions are very important in several major deposit classes or deposit models worldwide. I've listed some of them here. The main one we're going to be talking about is the intrusion related gold deposit model. However, these other deposit models that I've listed here are all in some way related to geological intrusions. The most important on this list is probably the porphyry copper deposit, since that supplies around 80% of the world's copper supply and is related to subduction. But these other deposit models are in some way related to geological intrusions, be it that the ore body is very close to the intrusion itself, or the ore body has formed through hydrothermal fluids that have been derived off of the intrusion. For example, in the VMS system at the bottom, if you've ever seen those black smoker chimneys on Attenborough programs, that's kind of what forms VMS, volcanic massive sulfide deposits. But the hydrothermal circulation that is responsible for that is being driven by the heat of geological intrusions at depth. The bottom line I'm trying to get across is that many ore deposit classes and models that we have in the geological literature, geological intrusions form a fundamental part of that model. And when it comes to tectonic setting, and you've seen this diagram on the right before because it's been in the previous presentation, where we want to be if we're going to be finding these intrusion-related gold deposits, we want to be in collisional tectonic settings. Collisional tectonic settings are responsible for most of the igneous intrusions that we would like to explore for, whether that is in our deposit model of interest or if it's in the porphyry model, because it's this process of subduction that is going to generate melting. It's going to generate magmas that come up that may underplate the lithosphere, and they themselves can constitute an intrusion. But that heat flow is going to generate more melting potentially within the continental crust. And when those crystallize at depth, that's the intrusion that we may want to explore for. But even not related to subduction necessarily, but if we just collide two plates together, if we thicken the crust enough, we're going to be able to generate more igneous intrusions just simply because of the heat flow. And that's kind of depicted down here in this diagram over here, which is kind of the post-subduction stage which is often responsible for the tin tungsten granites that were, say, down at Cornwall. But we want to be exploring within these collisional settings over here, be it a continental margin or an orogenic belt. But intrusion-related gold deposits tend to form post-collision, mainly within this stage over here. But the bottom line is that we need collisional settings if we're going to be finding the most prospective geological intrusions. So this is just a summary. You can read it if you like. But as discussed previously, we're going to be focusing on the Paterson region, as in the previous two presentations, because that's where Havieron is. And the Paterson region is a collisional tectonic setting, which is ideal for finding intrusion-related gold deposits. So I'm going to recap the Paterson, but before I do that, I just want you to point you to the fact that I have two previous presentations on this, and I go over in much more detail in those, kind of from start to finish, the geological history of the Paterson Orogen. So I don't really want to do it again here, so I suggest you go and watch those two videos for that, and for the extra content that's in there that's going to help with this presentation. But here's a geological map of Western Australia. The red square in the top right is the Paterson Orogen, and I've put the square kind of approximately where the next image on the slide is going to be. Now this formed in response to the collision between the North Australian craton and the West Australian craton. In view here is kind of the West Australia craton, which is made up of the Pilbara and the Yilgarn craton kind of sandwiched together, and that collides with the North Australian craton about 1.8 billion years ago through quite a long time, up to around about a billion years, where we have formed a supercontinent called Rodinia. But the period of interest we care about is the Neoproterozoic, because the Neoproterozoic is where the Ionina supergroup sediments are, which host the mineralization, which are deposited in this little bit here called the Ionina Basin. So this is just a zoomed in version of that red square. As I said before, this is the Paterson Orogen. We've got a series of major crustal scale faults that run through here as these black lines. We have a metamorphic basement called the Rudall Metamorphic Complex. Greatland Gold has a tenement named after the Rudall, so it's going to be interesting to see what they're going to explore for there over the next few years. But where the Havieron and all the other gold deposits are is here within this little red sort of blob, and that's the Ionina Basin, which has been intruded by a series of Neoproterozoic granites. It's covered by a bunch of Permian and younger deposits on top, but it comprises something called the Ionina supergroup, which is the sediments which host the mineralization. And that's split into two different groups. One's called the Frossal Range group, which hosts the Nifty deposit, and then you have the Lamil Group, which hosts the Telfer and Havieron mineralization. And here's the Lamil Group, just kind of in a bit more detail. It is a regressive sandstone shell carbonate sequence. Basically, it starts off as quite shallow marine and then progresses more towards shoreline and continental sediments. So we're basically drying out a basin, essentially. The Malu quartzites at the bottom, or the Malu formation, is what hosts Telfer. The Punta Punta is what hosts Havieron. Okay, and this whole thing's been intruded by a series of granites that are undeformed and quite highly fractionated. Here is a summary of all of that information on one diagram. I've presented this last time. Like I said before, we're located up here in the Lamil. We have our granites coming through into this formation around about 650 to 605 million years ago, which is coeval with kind of the end of the Miles orogeny. So that's basically the time frame which we're going to be looking to be exploring. We want granites that are within that interval, and of course we want to be looking for faults and things like that that are going to potentially be coeval with the breakup or the post-orogenic collapse of the Miles orogeny. And speaking of the granites, this is a couple of tables which you can see where basically we've got these red sort of blobs here that denote the intrusions as part of what is known as the O'Callaghan's Supersuite. It's sometimes referred to as the Mount Crofton Granite Suite, but the reason why I prefer the O'Callaghan's is because the O'Callaghan's is the youngest one, and the Mount Crofton tends to be the earliest granites that are more oxidized. The O'Callaghan's is mainly reduced, and I'll get onto what that it means in a bit. But I've just called it the O'Callaghan's Supersuite, but it is the same thing as saying the Mount Crofton granites. But you can see they crop out all over the Ionina Basin. They can be grouped, split into Mount Crofton, Minyari, Wilkie, and O'Callaghan's groups. There's a few unnamed that haven't really been assigned, but the point is we've got these Neoproterozoic age granites that are cross-cutting the Ionina group sediments, and ultimately these intrusions are providing the heat, the hydrothermal fluids, and possibly the metals into this wider area. And as I said before, this is the O'Callaghan's Granite Supersuite. I've relabeled some of the granites. We have the Mount Crofton granites in the top left, the Minyari is in the top right, the Wilkie granites, which are the most proximal on this map to Telfer and Havieron, are marked here. But no matter which one you take, they are all what we call I-type granites, which stands for igneous type granites. So these are granites that are being formed through igneous processes or remelting of igneous rock. That's in contrast to what we would refer to as S-type granites, where if we melt sediments and form granites, then of course it's called S-type. We can also split this up into whether or not these are reduced granites or oxidized granites based on the presence of either magnetite or ilmenite. Ilmenite series granites are reduced granites, and only the O'Callaghan's is an example of that. Most of these granites are oxidized granites because of the presence of magnetite in the magnetite series. Now the granites range in age from 650 to 605 million years. The oldest granites are the Mount Crofton and Wilkie granites, 645 in this table by this paper over here, and the O'Callaghan's is the youngest at 605, which is more reducing. So it appears that over time, these granites have started as oxidized and have now become reduced over time, which could reflect a change in magma composition or potentially different reactions with the wall rock. And here is a summary of all that information I've presented previously. Feel free to pause it and read as you wish. The Miles orogeny time frame is a little bit debated in the literature, so I've just quoted this one here. But the bottom line is that the tectonic setting, the local geology, and the fact that the granites are I-type provide a prime environment for intrusion-related gold deposit targeting, which is what we're going to be focusing on here on out. So that brings us on to intrusion-related gold deposits. This next section is going to focus on their characteristics and how we can apply that to the Paterson Orogen. So, intrusion-related gold deposits then. So intrusion-related gold deposits represent zoned magmatic hydrothermal ore systems. These deposits are often located at cratonic margins, in orogenic belts, and rarely in back arc environments, although I would speculate on that one, and are related to extensional processes, which seems a bit weird because I've been talking a lot about collision. So where does the extension come in? Well, the extension comes in a process known as post-orogenic collapse, depicted on here as post-collisional extension. Now, the major mechanism that I understand that controls this is the fact that during the collisional tectonic setting, either through continued subduction or mainly through two plates colliding, we thicken the crust. Now, as we thicken the crust, as it gets thicker and thicker, it's going to start to destabilize under its own weight. And as it starts to destabilize under its own weight, it's going to start to collapse in on itself, and it's going to generate extensional tectonics, or possibly even a little bit of strike slip. And as a result of that, we're able to open up crustal scale faults, fractures, and that is the accommodation space or the pathway in which many of these intrusions in hydrothermal fluids can pass up. But to generate the intrusion, we undergo a process known as decompression melting. Because if we create an extension, we can rise the asthenosphere, or we're going to lower the pressure in the subsurface of the Earth to the point where we can melt rocks, and that's going to generate these intrusions that can pass up these faults and intrude higher up into the crust. And in this diagram, you can see they've split it up into four subtypes of intrusion, into four subtypes of deposit rather, and it's the intrusion-related gold deposit we're interested in. And these are typically associated with moderately reduced I-type intrusions. So these are igneous derived plutons and granites that are coming into metasedimentary rocks, because typically this is after we've metamorphosed the regional stratigraphy, and that these are moderately reduced. That means that they don't have a high oxygen activity, and I'm going to get onto that in a couple of slides' time. So this slide is going to go over some of the specific characteristics of intrusion-related gold deposits, which are going to help distinguish them from perhaps porphyry copper deposits and orogenic gold deposits, because to be honest, they borrow characteristics from both. Some people out there might be thinking, well, aren't these just porphyry copper deposits? The key difference between intrusion-related gold deposits and porphyry deposits is, one, the composition of the magma. So in the porphyry copper, we tend to get much more oxidized melts, whereas intrusion related, we're a little bit more reducing. The fluid chemistry that's derived off of those plutons is different, and the metal associations are slightly different as well. So intrusion related gold deposits often have a gold, bismuth, tellurium type signature, as well as tungsten, arsenic, molybdenum, and antimony. We don't really see some of these metals, for example, in porphyry copper deposits or even orogenic gold deposits. We have what is referred to as pyrrhotite stable conditions. You'll know that pyrrhotite is present at Havieron, for example. This is a sulfide mineral that often indicates more reducing conditions, and this is a common sulfide that's present within intrusion-related gold that you might not get in other deposit models. In general, though, the sulfide mineral assemblage is actually rather poor, less than 5% of the overall rock volume. But we normally get chalcopyrite, pyrite, obviously I've mentioned pyrrhotite, as the sulfide minerals, but also potentially the presence of galena and sphalerite. They often crystallize much later on in the overall paragenesis of the deposit. The fluid chemistry is quite diagnostic. Normally we get what are called carbonic fluids, and that denotes the presence of CO2. These are quite CO2 rich fluids that come off of the intrusion related gold deposit pluton, which is a little bit different to what we get in the other ore deposit models. And normally these intrusions occur between crustal depths of 4 and 6 kilometers. Now I've kind of zoomed out this image from the previous slide. You can see that the intrusion's kind of along a fault, a crustal scale fault. There's a variety of different deposit styles around it, much like porphyry. We have skarn type deposits, we have mineralization within the intrusion itself, sheeted veins, veins that are located distally, and you'll notice the presence of these silver, zinc, and lead fissure veins, which is kind of very similar to the metals that we're getting at Scallywag. And just lastly, this top diagram, this kind of shows you a rough genetic model for how these type of deposits can form from Dave Groves. We're in a collisional tectonic setting, maybe with or without a subduction zone. We are in the post-subduction environment, basically, where the mantle or the lithosphere above that subduction zone has now been modified by the process of subduction, making it nice and metal and volatile rich. If we melt that and then put that melt into the upper levels of the crust, we're obviously taking metals and volatiles into that portion. The hydrothermal fluids that can exsolve off of that can scavenge metals and obviously emplace those as hydrothermal ore deposits or magmatic hydrothermal ore deposits. And this environment up here is where we're going to be getting our intrusion related gold deposit. So I've spoken a lot about oxidation state, and this is why. The plot on the left hand side is from a paper by John Thompson in 1999, a prominent economic geologist, and it shows you the iron content of magmas as a percentage on the left hand side of the graph, and then on the x-axis whether or not the magma is reduced or oxidized based on the activity of oxygen. Now what happens where we get an oxidized melt and a high iron content, which is typical of iron oxide copper gold and porphyry copper gold systems, is we get gold associated with more chalcophile elements, that is copper in this oval. But if we become more reducing and have less iron contents in the magma, we move this way towards more tin and tungsten, which is what Cornwall granites are. Now, in this sort of oval shape here, that is kind of given here, this is the iron oxide, this is the intrusion related gold deposit box. You can see it kind of straddles the two end members, because that shows you that the intrusion related gold deposit pluton, we want to be finding moderately reduced plutons that are more ilmenite series than magnetite series that are found in collisional tectonic settings and are producing metal associations that are more along the lines of tin, tungsten, and lithophile elements rather than chalcophile copper elements. And the diagram on the right is an extension of this diagram where we can see that with increasing distance from the subduction zone, we get more tin and tungsten, whereas closer to it, we get more copper. But also this thing about black shales. Now, black shales are reported at Havieron, and that may explain why we get less copper there as opposed to, say, Scallywag, where there are no black shales reported, because the increasing proportions of black shale change the metal composition more from copper down towards molybdenum. Okay? And there are a number of other key features that can affect the metal associations in an intrusion-related gold deposit. These are crustal depth, whether or not the granite is more fractionated. So if we have a more fractionated granite, that is to say that it gets more granitic. We have more tin tungsten associations, where if we're sort of less fractionated, more granodioritic, for example, we have more copper gold associations. The distance from the pluton itself, and this is kind of what this diagram on the right is showing you, will change what we get in terms of the metal associations, and we refer to that as zoning. So the central pluton, we'll get the gold, bismuth, tellurium, and tungsten, but away from that, and more distally from the pluton, whether that's related to time or whether that's just through simply the alteration that's being caused by the pluton, we zone outwards into arsenic gold, arsenic antimony gold, and silver, lead, and zinc. And I've mentioned this before, but that's kind of what we're getting at Scallywag by the looks of it at the moment. The local geology can have an influence. So if we, like I said about the black shales, if we've got more black shales, that's going to start to produce more reducing fluids. And then there's a timing question. As you'll see in later deposit examples, there can be multiple intrusions that are passing through at one go, and only one of those may be mineralized. Just going back to the crustal depth, and it's the crustal depth that affects which fluids we get. So the deeper the intrusion is, we tend to get more CO2-rich fluids, whereas the more shallower we go, we get more water-rich fluids. And it says about low salinity here, but really the water-rich fluids are much higher salinity than the carbonic fluids, which are found at depth. And in general, when we remove the CO2 from the fluid phase, we're going to leave behind a water-rich magmatic fluid that can gain salinity over time and become more like a brine. So in general, we get lower salinity carbonic fluids at depth, higher salinity water-rich fluids and brines in the shallower environment. But it's these carbonic fluids really that can take out the gold initially as what we call bisulfide complexes. And they will then destabilize with reactions in the wall rock higher up to then deposit the gold. It's a little bit of chemistry there, but I won't go too much more in detail. Now, the red circle denotes the rough paleo depth or the crustal depth at which most intrusion-related gold deposits occur. So that can affect the deposit style we get. We typically get sheeted veins, mineralization within the intrusion itself, stockwork veins, but also Breccia pipes, which is very similar to what we get, what looks to be getting around Havieron and the wider Paterson Orogen area. We may also get some skarn deposits, but basically the bottom line is we're intruding at between 4 and 6 kilometers and producing carbonic fluids and magmatic water-rich fluids off of the intrusion. And this is just a summary page, kind of illustrating all of the unique characteristics of intrusion-related gold deposits. The diagram on the right is more of an exploratory diagram that shows you that you can actually get reduced intrusion-related gold deposits and oxidized intrusion-related gold deposits, although the oxidized intrusion-related deposits do encompass a lot of porphyries, which is a separate deposit class, so it can get quite confusing. But feel free to pause it, read through this, because these are the characteristics that you would want to see in your granites in the Paterson if you're going to find an intrusion-related gold deposit. We're now going to move on to some examples, and we're going to start right in the Paterson Orogen with the Havieron target. So we're going to start with Havieron, which I don't think I need to spend too much time describing, as I think we're all quite familiar with it. If not, then please go and see some of the other presentations I've produced. The host rocks are the Punta Punta formation. We've got a lot of carbonate in there, which is obviously reacting with some of these hydrothermal fluids. An initial mineral resource estimate at 4.2 million ounces that I believe will most likely grow over the year, since it was based mainly on the South Crescent Zone and part of the Northern Breccia, We didn't include the eastern breccia or the northwest crescent, which if they added will likely increase this. The mineralization style, as we know, is breccia, vein, stockwork, and massive sulfide replacement, consisting primarily of chalcopyrite, pyrrhotite, and pyrite. There are multiple breccia targets and sulfide-rich crescent zone. As I said, more details, but this is just the plan view as explained in the RNS in October 29th. Heavily drilled now, excellent intercepts of high-grade gold intercepts, and good widths in the drill hole. And here's a table that I've used in a previous presentation to kind of show you the comparisons between Havieron, iron oxide copper gold, and Telfer type. Pretty much Havieron has very similar characteristics to Telfer, as indicated by the green here. It's worth pointing out that we've got this breccia class and wall rock, quartz carbonate sulfide veins, vein and breccia style mineralization, lack of iron oxides. It does say absent to rare anhydrite and potassium alteration, although from further reading there is potassium alteration present in both systems. But this table kind of shows you that what we're dealing with at Havieron is a Telfer style mineral deposit, which by and large is an intrusion related deposit. And here's just another slide giving some extra Havieron info that's not in previous presentations. Obviously, we've now produced a mineral resource estimate, so we've got some more detailed cross sections where you can see multiple drill intercepts of gold in a kind of cemented breccia, but also the crescent sulfide zone in purple kind of running along the edges of that. We get three types of breccia at Havieron. We get a calcite cemented breccia, an actinolite cemented breccia, which is a little bit unique, I've never heard of before, and a crackle breccia. In past presentations or past pieces of work by Newcrest, they identified three fluid inclusion types in quartz veins at Havieron: water-rich, carbonic and water-rich, and hypersaline inclusions, which I've just shown in the previous slides, that's the typical fluid compositions of intrusion-related gold deposits. It is also very similar to Telfer, where there were 5 different fluid inclusion types, and these 3 were present there as well. Now, the timing of the intrusions and some other characteristics with comparing Telfer and Havieron are not as certain. The timing of Havieron may be later, we're not really sure, but the point is that the fluids are very similar to those at Telfer and other intrusion-related gold deposits. So moving on to Scallywag, this is a diagram on the right just showing you the latest magnetic map and drill hole locations from the latest RNS. The drill holes are in as the black dots, and obviously the various magnetic targets, London, Kraken and Blackbeard. Now, it was revealed in the RNS that we actually have a syncline here. So it's not an anticline. The anticline's at Havieron. So we have basically a syncline-anticline pairing, where obviously in an anticline we have the oldest rocks in the core. So over here at Havieron, the Punta Punta will be in the core, but then that will fold around the outside of the Scallywag syncline. So actually that explains why Kraken intercepts Punta Punta much more easily than London and Blackbeard. We also, based on the soil geochemistry, looks like we have a more copper gold system, the gold copper system at Scallywag as opposed to Havieron. Here are some of the key finds then. We've already gone over this in the very last video, but just to put it up, they have a few samples, 16 samples with more than 5 part per million bismuth, 16 more than 200 part per million in lead, blah, blah, blah. Basically, these pathfinder elements, bismuth, arsenic, silver, tellurium, lead, if you remember back, this is very similar to what you'd expect in an intrusion-related gold system. You want to see enrichments in that above what you would typically expect in the background. We finally got the presence of a granite sill in one of the drill cores. Now, where that's coming from, what the timing is uncertain, but the fact that we've actually got some granite in the drill core as opposed to this inferred granite, which really is only on the Artemis presentation, is kind of direct evidence that we have a granite that is basically supplying the heat and everything else to the system. This is kind of the first direct evidence of that. Whether it's this particular sill, whether that's a late one or an early one, we don't know. We have quartz, pyrite and hematite veins, which suggests a more oxidizing environment. But quartz, pyrite and hematite is often an alteration zone. And I say that because this is a report from Newcrest in 2009, and what they showed when they were in charge of Havieron back then is that they managed to drill through a distal alteration zone that they described as hematite dusting and chlorite. It tends to get more calc-potassic and potassic towards the center, and that hematite obviously being at Havieron there is kind of analogous to what we're finding at Scallywag. Also, this plot on the right from Hart 2007 shows that with increasing time, or increasing distance, if you like, away from the Pluton, we're tending to get lower temperature lead, zinc, silver veins. And we've got enrichments in lead and in some cases zinc in some of the drill results that we've got from Scallywag. So it looks as if Scallywag has drilled through a alteration zone, a distal alteration zone. And this line here that says both pervasive and selected styles of hematitic alteration are associated with peripheral zones of mineralization. That was a comment made about Havieron. So it's not too much of a leap to assume that that is very similar to what we're getting at Scallywag. I'm now going to move on to some analogues to compare what we see with the Paterson Orogen to some other intrusion-related gold deposits worldwide. So we're going to stay in Australia first and go to somewhere called the Kidston deposit. It's located in the Georgetown Inlier in Queensland, and it's a Carboniferous aged breccia pipe that was created by the intrusions of a bunch of rhyolite dikes into Proterozoic aged metavolcanics. Okay, the total gold production was around 5 million ounces, mostly within the upper 250 meters of the pipe. It has a very similar ore mineralogy to what we see in intrusion-related gold deposits near Telfer and elsewhere, and also the alteration is very similar. So the breccia pipe analogy is kind of very similar to what we're getting in some regards to Havieron. But one of the other keys with this deposit is that the gold is only hosted in the post-breccia timing. This diagram on the right, which you can't really see very well, shows you a breakdown of all the different stages of this breccia pipe formation, and it's only in the post-breccia realm that we really get the gold. So this is why timing is really important when it comes to exploration. Okay. So in terms of how breccia pipes form, basically we get an intrusion, we exsolve fluids, and if those fluids are highly pressurized, we can overcome the lithostatic pressure above, and basically what we can do, especially if there's faults already present, we can exploit those and start to essentially collapse the overlying stratigraphy in on itself, especially if there's carbonate present, because we can also dissolve that as well. And that's what the diagram on the left-hand side shows you. The diagram on the right is just a colored version where you can see various chunks and clasts collapsing in on itself. Some of these, if there's already been mineralization occurring, may already be mineralized, but any metals and hydrothermal fluids may crystallize metals around those clasts or potentially even replace them. But moving outside of Australia, we can go over to Canada, and I found a very, very interesting deposit named the Malartic district. Now, this is a really well-studied deposit. There is an extensive amount of literature, and I've only really scratched the surface, and I haven't really got time to explain everything about that, even with that. But the bottom line is, this is a very old deposit. This is Archean, so this is even older than where we are in the Paterson. But it's a world-class intrusion-related gold deposit that has actually had a total endowment so far of 16.3 million ounces, right? The actual resource estimate, I believe, is 10.8 million ounces when it was finalized in their feasibility study. So that just goes to show you that a 10 million ounce deposit is an exceptional find. The host rocks are metaturbidites. These are basically metasediments. Again, very similar to what we see in the Paterson. Now, this one's actually classified as an oxidized intrusion-related gold deposit. It has an oxygen fugacity, if you like, or the activity of oxygen of -19, which is still right on that border. If you go back to the previous diagram I showed with the oxidation state, you'll see it's right on the border, but they characterize it as a slightly oxidized intrusion-related, which is different really to what Havieron, because this does not have much pyrrhotite, if any at all. It's run by Agnico Eagle, a major miner in Canada. And the Malartic is located in the Superior province, which is known for it's one of the most mineralized provinces in the world. It's a geological paradise. And here is a more detailed geological map produced by Gaillard in 2020. What this shows is you can see along this major deformation zone known as the Cadillac-Larder Lake Deformation Zone, we see a whole bunch of different mineral deposits ranging from orogenic gold or lode gold to gold-rich VMS sulfide deposits. We also hear Malartic's located over here, okay, which is an intrusion-related gold deposit. But all the way along, we get different mineral sort of deposit models located and concentrated along this deformation zone, such as Kirkland Lake, which is a company on itself, and like Sigma Lamarck, which is a very gold-rich orogenic gold deposit. But the point is that we've got a bunch of intrusions passing through metasedimentary rocks located very close to a crustal scale deformation zone. And here we have the Artemis resources interpretation of the Havieron area, and obviously their targets. Now they've picked out a granite that could be exposed at depth on a seismic line, but the other key feature is obviously the presence of these thrust faults, namely the Havieron thrust fault that runs around like this into the Scallywag area as well. Now if you think back to the last diagram where we had that big deformation zone called the Cadillac-Larder Deformation Zone. Now this may be a smaller scale version of something like that, which could act potentially as a focusing point for hydrothermal fluids and can lead to ore deposits that are forming either on or close to this particular thrust fault. So in many ways, this interpretation is kind of very similar to that is exposed in Malartic, maybe just on a smaller scale, and definitely should require further investigation. Now, the key reason why I picked out the Malartic district is because of how well studied it is. It has been shown that there are a variety of different methods that can be applied in the rocks around the deposit that can potentially what we call vector towards the ore deposit itself. And that's what this diagram on the right shows. This is showing you a bunch of different sort of observations that have been observed from moving further away from the deposit up to 5 kilometers towards where the ore body is. And the major one that is kind of talked about in the literature is the fact that we see a change in the alteration and we see a change in the metal associations. Okay, so the alteration tends to be more carbonate and potassium sodium alteration proximal to deposit, but becomes much more kind of hematitic and less potassic away from the deposit. Okay, and this was a key finding of the Gaillard paper, was the fact that we get enrichments in these compounds, carbon dioxide, gold, tellurium, tungsten, silver, and these increase towards the ore zone as opposed to away from the ore zone. We also see a change in deposit style where we get quartz carbonate veins, disseminated pyrite and sulfide replacement much closer to the deposit, where we see less of this further away. So what we can do is, obviously, if we have a bunch of rocks that are out here, we can look at the chemistry of those, and then if we're lucky enough to drill in a location that's closer to the deposit, say here, we will see an increase in particular elements towards the ore zone. So we will know that we're heading in the right direction. This, in combination with better geophysical techniques and potentially some mineral chemistry like here, such as tungsten-rich rutile, which is definitely present in these areas, we can perhaps get closer to where the ore deposit is, known as a vectoring. And this is the approach that should be being taken at Scallywag. And just to follow up on that, this is a diagram on the right showing the classic alteration zones that you get in porphyry copper systems. These have been explored for a very long time, more successfully than probably any other deposit type with this approach, because we get diagnostic alteration zones. Most distally away from the intrusion, we get something called propylitic alteration, which has a very particular mineral assemblage and metal association, whereas proximal to the deposit, we get much more potassic alteration and more potassium feldspar. So we can see that in the rocks, and we can obviously take rocks from out here and take rocks from in here, and we can see those changes over time through the rocks that are exposed. And as I said, this is the approach that should be being taken at Scallywag. And I've just taken some quotes out of a paper, the same paper, that Gaillard paper, that really emphasizes this point. It explains that major gold deposits in metamorphic terrains are typically surrounded by extensive wall rock alteration halos manifested by systematic changes in mineralogy away from the hydrothermal fluid pathways. Basically, we get a change in the element associations with increasing distance from the center. It explains that the natural zonation of alteration reflects the progressive decrease in fluid rock interaction. So the further away we get, the less reactions with the wall rock we're getting, so the less kind of changes we're going to get. And it says that because the variations in alteration mineralogy are generally commensurate with mass transfer, lithogeochemical data can be used to assess the magnitude and spatial distribution of fluid rock interaction. So basically, lithogeochemistry, we basically take some rocks and we basically pulverize them in the labs, and we'll get a full suite of elements out of it. And the key elements, it says, are ore-related pathfinder elements such as tungsten, tellurium, antimony, bismuth, or arsenic that can delineate lithogeochemical anomalies that extend far beyond the limits of the hydrothermal alteration. And at Malartic, it has been found that the lithogeochemical halo around the ore deposit can be around 10 kilometers in length and 2 kilometers wide, which means that if we're distal at Scallywag, we could be a few kilometers away, maybe 2 kilometers in width, 10 kilometers in length from the major ore deposit. Last thing, the Lassonde Curve. Okay, so the Lassonde Curve just describes the life cycle of a junior explorer, or actually, more specifically, in my opinion, a specific project within a company. So obviously, Scallywag is in the exploration stage. It's in the earliest part. Okay, it's probably in this part here. We're pre-discovery. Havieron is way further along. We're actually probably in the development stage now. We're rising up the curve. We're in the engineering and construction phase, pretty much. So you've got two different things here. So it is completely illogical, really, to compare Havieron with Scallywag now. Okay, you can compare the journey. The thing is, with the GGP, they hit Havieron first time. No bad results. Here at Scallywag, we've drilled away from the ore centre and have found alteration. Now it's the task. Now is where the real exploration begins. Now is where we're going to be seeing more drill results and hopefully an increase in those pathfinder elements and gold grades go alongside it. Okay. Now, based on what I've explained today, and that brings me to the end of the presentation. Here are the conclusions. You can spend some time reading it. The key things that I want to point out is that the pathfinder elements and lithogeochemistry can provide a key exploration tool to narrow down the search for a major ore find, much like what we see at Malartic. Scallywag is showing very similar alteration chemistry to Malartic and other intrusion-related gold deposits worldwide. I have a slight hypothesis that suggests that Scallywag could potentially be a bit genetically different to Havieron and Telfer in terms of the metals and the timing. That's just simply based on the fact that it seems to be more copper rich, and also the fact that because of that, we may be having a slightly more oxidized granite as opposed to reduced granite. And obviously that Scallywag is very early on the Lassonde Curve, so we need more data and we need more exploration to help verify this up, whereas Havieron is much further along and more de-risked. I'd like to thank you for listening to the presentation. I'm going to possibly do a live stream in the future answering any questions you may have, because I think it will be worth the time to do that. But apart from that, thank you for watching and see you later.